Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. My name is Lee Dirks, and I am the Director for Education and Scholarly Communication at Microsoft Research. And it is my pleasure today to introduce two speakers who will be joining us from Cornell University's Department of Information Science. One is a long-term colleague and collaborator, Dr. Carl Lugosi, and his colleague Bernard Hasselhofer. They will be talking to us today about research on scholarly practices and communication at Cornell Information Science. And I'd like to introduce and welcome to the podium, Carl Lugosi.
Thanks, Lee. Thank you all for joining virtually and physically. I really appreciate it. I'm going to talk about, give an overview today of work we've been doing at Cornell in scholarly practices and communication. I'm going to start off, I'm going to dabble and bounce around some research projects we've been involved in, motivate the work. Bernhard's going to follow up, who joined us recently in March, to talk about the work that he's doing, and we'll connect those all under one umbrella. If you people in the audience have any questions, please feel free to ask or comment at will. So I just very briefly, I always feel the need to evangelize and advertise Cornell Information Science, which I think is a very unique entity. Our view of information science is really built around these three hubs here of dealing with technology, information systems, human-computer interaction, so how humans interact with the technology, and how the social rules and cultural norms interact with all of those things. So we really bring together technology, people, and society together under one umbrella. We advertise ourselves as the information school that was never a library school. So you could say that has good aspects and it has bad aspects. But the nice thing about our program is we link all the way out on campus to a whole bunch of different types of areas, including law, computer science, psychology, and other things. So it's a really interesting, it's a new program. The department's been in existence for about 4 years now, and I'm really proud to be a member of it, and I think we're making great strides. The people whose work I'm going to be talking about today is, of course, as Robert Walensky, my colleague at Berkeley, once said, he does the PowerPoint and the rest of the people do the work. So it's Bernhard, who recently joined the work, Yuk-Young Jo, who's a PhD student in computer science, Karen Patsky, who's a first-year information science student in IS, Teresa, who is finishing up her degree and going to join me as a postdoc, and then a few other people, including Paul Ginsberg, who you might know, who's done the major work on archive, and Simeon Warner, his colleague. So a bunch of great people. And sort of to set the stage, many of you might know David Levy, who's a faculty member in the Information School at University of Washington. Lee, do you know David?
I know the name, but
Yeah. So David, as a CS PhD from Stanford, he describes himself as a computer scientist who went astray. And I find myself more or less being in that position. The background of my work is highly technical. On the screen here are a bunch of projects that I've been involved in. Digital Libraries Initiative, I did a lot of infrastructure work there. I created a system called Ancestral, which was a infrastructure for technical reports on the web. NSDL, a National Science Digital Library, partly responsible with Sandy Payette for Fedora Commons, and Open Archives Initiative, and work that was highly protocol-based and technology-based. And after years of working in this very technical manner, I continually got frustrated as to why the work was being adopted by a limited number of audiences, but not going in sort of large-scale deployment. And that led me to think more about what's interesting about infrastructure, what is it that really makes it difficult to develop infrastructure that really works across a bunch of different communities. And why are we trying to drive things with technology when all of the standard paradigms of how technology permeates society are these sort of socio-technical, socio-cultural models? So I've begun to think a lot more about that. And the recent work I've been doing with people in my group is understanding how to resolve cyber infrastructure and scholarly culture. This, by the way, is the Mial Bridge. If you've not seen this, this is a bridge in France. It's one of the great architectural wonders. So that's not a science fiction picture, it's a real bridge. So what I want to talk about today is some aspects of this research and look at it from the top level and understand what the problem is. And this work stems from this sort of broader vision of interoperability and how do we make systems work across different cultures and different domains. And of course, our standard Tower of Babel view here. How do we get a technical protocol that works amongst people that work in very different manners? So the foolish among us, where I talk about myself years ago, were naive to think that this was a relatively easy problem, that you came up with a protocol. And this is a paper that the late Barry Leiner published on some work that we were doing that came out of Cornell, which is this open architecture for the worldwide digital library. And this view that we could come up, that information and knowledge and information habits could be fit into a single architecture was something that we naively thought in 1998. And since then have sort of rethought and understood more of the complexities. A lot of people that I proudly joined a large number of people who thought that there was going to be sort of the web was going to come along, and that these architectures were going to come along, and the world was suddenly going to change. The revolution was going to happen, and I always hate to keep overusing Stephen Harnad's name, but Stephen is my poster child of someone who would get up and say, "Look, physicists did this. Everybody else is going to do it any day now." And this is. Excuse me for him holding an iPhone. It's not my picture. But this notion that the revolution was inevitable as soon as we deployed this architecture, and everybody was going to change, and all these issues with intellectual property and scholarly cultures were going to go away, was really obviously false. And it really pretended that scholars were sort of a bunch of sheep, that they just sort of did things in, sort of en masse and got themselves shaved in the same way and herded in the same way and bought in the same way. And the reality is that adoption of these technologies really varies. It varies from relative disinterest, like why should I care, to slightly more violent reactions to I don't care, I don't want it, and this is what I think of it. So we have found through the years, and I'll be talking about chemists, not that this is my representation of chemists, but there's a lot of reactions in a lot of communities that we simply don't want this. It violates what we want. You know, an interesting thing is I'm a real fan of citizen science. And get up and talk about citizen science in some venues, and they will literally start throwing mud at you. Don't you realize that violates the basic notions of how science is done in professional science? So this very clear difference in understanding these different communities is very important. So if you haven't seen this is, I think, one of the best documents available. This is a white paper that came out of an NSF workshop on understanding infrastructure, dynamics, tensions, and designs. It's a wonderful paper that talks about how difficult this phenomenon called infrastructure is to develop. And it uses a lot of historical precedents, such as railroads, banks, the banking system, the electricity system, and the telephone system. And it really points out this basic socio-technical paradigm that the path between technological and the social is not static. There is no one correct mapping. And cyber infrastructure will only develop when social, organizational, and cultural issues are resolved in tandem with the creation of technology. That you must approach this difficult thing of society and culture at the same time you do the relatively easy thing of technology. And I say relatively easy to quote the late Jim Gray, who said, if only all of our problems were code. So that's the sort of the work, the basis of the work that we build upon. And really, when we look across science, we look across scholarship, we see a bunch of different islands that really segregate them in interesting ways. We see these strong methodological islands. People do different scientific methods, and the scientific method varies, and the technology has to vary with them. Epistemological knowledge, the general way they view the world, their notion of knowledge, and the cultures that have developed. And these are all sort of independent dimensions that we need to understand. So the way you start this research is trying to understand what is the analytical unit. I mean, a basic research problem as you're looking at this issue is what are you calling what are you defining or attaching the word culture to? Is it a discipline? And I think we'd all agree that the discipline is actually really, it's too coarse of a granularity. Of course, you can say chemists, and suddenly you have synthetic chemists, you have theoretical chemists, you have physical chemists, and the same thing across a lot of other disciplines. Is it a subdiscipline? Well, I don't think that works very well either. Is it a research group? And that sort of gets you down to the level of impossibility, because if it's individual research groups, you can't do much of anything. Or is it this thing called the invisible college that other people have used as a term to describe this group of people who collaborate across institutional lines in some unique manner? So the issue here is to understand that, and the issue is to pick a really interesting community to start your research on, which is chemistry. Chemistry is a particularly challenging area, right, Mark? That's right. We have spent about the last 3 or 4 years looking at chemists and working with chemists to understand why this is such a difficult area. And some things that stand out about why it's so difficult is the commercial value of chemical information. I mean, astronomers will tell you that our data, what's wonderful about our data is nobody would pay for it. That's certainly not true of chemical information, especially in the pharmaceutical industry. And then there's just the nature of the research culture. You have this predominance of this thing called synthesis, this creation culture, which overshadows discovery. Really, the concern here is not to discover, to look at the world, it's to figure out how to make new things, and these sort of secret methods of making new things. And that leads to a highly autonomous culture in which successful research really relies not on a lot of other people. It relies on being in a lab and figuring out how to get these things to work together. And then there's the really difficult problem of the scholarly societies. The ACS, particularly in the United States, the American Chemical Society, is simply violently opposed to open access, and violently opposed in many ways. And people always love this who don't know this. The core identifier system in chemistry has copyright issues attached to it. You cannot use the identifiers without paying the ACS for use of the identifiers. So it's kind of hard to build infrastructure if you can't share identifiers of objects. And then the RSC is considerably better, but still has some licensing issues, but they're getting better. So just to go back to the historical notions of some of the things that have happened here, one of the things we looked at the beginning of our work is this question. In physics, the archive came along with phenomenal success. Paul Ginsburg invented it in 1991. In higher energy physics, and it advanced from there to other fields of physics, it became the venue for publishing. It basically changed the way they published. When they tried to do the same thing in biomedicine, it became highly modified, and the hybrid looks very little like the original model. And in chemistry, it crashed and burned. The attempt to have an archive of chemistry literature, just open archive, went away. The societies basically tried to shut it down. So, we have to ask why these things happen. So, for a really big overview and I can compliment this work even though my name's on it because it's mostly Teresa's work. My student Teresa and I led an NSF workshop in DC about 2 years ago, and out of that came 2 papers, a Nature Chemistry article and a longer white paper that the URL of that is included in this. And this really points out it gives a very long, very highly detailed analysis of what is the problem with chemistry, what's going on here. And it talks about the technology, it talks about the culture. So if you're interested in this subject, I recommend that you take a look at these. That's the handle to the paper. Okay, so how do you study this problem? I mean, we can all sit here and we can do back of the envelope or our napkin, or writing on the napkin, sort of, okay, disciplines differ, how do we understand this? But really, this requires sort of innovative methods to understand why this problem exists. So I'm going to talk in particular to some work that Teresa and Asif Al-Haq and I have been doing that this paper published in Science Metrics talks about, is to understand the fundamentals of the problem, to understand why this problem exists, and where we might go from here. So, so to ask basic research questions like, how do the socio-intellectual characteristics of the field shape the communications that they carry on? How does the communication culture reflect the practice culture, and how do they interact, and what's the synergy between them? And how within a field such as chemistry, how are there differences within the fields itself? So we've adopted, I think, a very innovative approach, which is to combine ethnography and network analysis, and to take advantage of the strengths of each. So ethnography is great, but the problem with ethnography is it's very expensive. It's very, very labor intensive, and a classic ethnography study can only study a few groups. Network analysis is great because you can take huge amounts of data, but the problem is that the nuances and subtleties you do not see the nuances and subtleties. So what we try to do is to try to combine those two techniques with one enhancing the other, and I'll talk about how that's done in a second, to come up with a mesoscopic level of analysis, to understand the co-authorship relationships and how they cluster and the relationship between those clusters, to understand what collaboration patterns are in chemistry. And we're trying to understand how collaboration patterns reflect communication cultures reflect collaboration patterns, and how technology might either interfere or enhance those collaboration patterns. Because if you don't understand the way scientists work together, you're not going to be able to have technology to allow that, to enhance that. So here's an overall view of the technique, and the technique is as follows. I think I can get a pointer here. I thought I could get a pointer here, but I can't get a pointer here.
You got a laser pointer too.
That thing. And the pointer goes like that. Whoop! Okay, so the basic technique looks like this. We, on the left-hand side are the ethnographic field studies. On the right-hand side is the network analysis. And we do basically a delineation of the field. We understand what the units of analysis are. We then bounce from that, and we do an author and field citation network within that individual field. We then bounce back and do we analyze. We sit on some main labs in that group and work with them to understand what they do, and then develop co-authorship networks in those groups, and reflect in those groups, and the leaders of those groups. We take the networks and we bounce them back and forth, and have them look at our clusterings and understand what they mean to them and how we might modify our clusterings. And we use this bidirectionality of going from ethnographic to network analysis back and forth to come up with a synthesis of field differences in the cultures. And the technique works really nicely because you get these aha moments in which actually a researcher will look at a clustering that you've done and say, hey, that person there reflects what we're doing. That sort of pattern reflects what we're doing, without us trying to infer from it information that is really cultural. So the work we've done has studied 5 labs in 2 major fields, and this field here included synthetic chemistry, theoretical physics, and experimental physics. So these sort of existed, and this was a mainly what we call an instrument building culture. This was a field of chemistry that relied on building large instruments and using those instruments. And this was another field that was that includes inorganic chemistry, polymer chemistry, and organic chemistry. And this was a more synthetic culture that did substance building. And this picture leads to the breakdown in the analysis and the collaboration patterns that really are based on these 2 notions. People who work with large instruments that cost a lot of money, that take a long time to develop, and people who work with creating substances in individual labs. And we'll see very different collaboration patterns in the 2 of them. So we spent a lot of time with those people. We attempted to understand their research cultures. What are the valued skills in their domains? What is competence? How do they share information? And from there, came up with some interesting analysis that I'll talk about in a moment. So to go from the fields to actually doing the network analysis, we worked with the leaders of these labs to develop a lexical query into the Web of Science to come out with a co-authorship graph. So what we wanted to do was develop a co-authorship graph, a clustered graph that basically represented the field. I'm sorry, a citation graph that represented the breadth of the field. And we wanted to come up with something that had actually the recall and depth in the field, and we could use article self-citation to understand if we were getting enough depth. That the query revealed the things that Carl Agozzi published and cited on himself, and then the breadth to actually cover the people that I would collaborate with and reference. And it's a rude and crude method, but we've basically come up with a notion that this is really a good way, using the bibliographic mapping and the citation map is a really good way to delineate these units of study. And what comes out of that is a huge citation network that we then use to create a co-author network. And we then classify nodes in the cluster and compare the clusters with field observations and interview the group leaders and try to figure out whether these graphs represent what they think of the world. And what's interesting when you do that, you come up with some very nice patterns. So I put up here 3 different topologies of groups that represent collaboration patterns. And here you can see what stares out at us as a classic PI-led research group. So this is a co-authorship graph. Again, the nodes are authors and the edges are if I've co-authored with you. And here's the strong leader who insists that every paper be published with him or her. Here's the research institute. I would think that Microsoft Research sort of looks like this. That you have people who you walk down the hall, you say, oh, we have similar research, you start to work together, and then you co-author with each other. And then here you have an international research network where you have PIs in separate countries and you have some crossing boundaries across there. So we have a bunch of topologies like this, and these topologies, you can reflect these topologies again back in the ethnographic studies, and people look at them and say, hey, I know who that is, and I know who that is, and things like that. So what also comes out is if you analyze this at the mesoscopic level, is you start to understand what the roles are of different people in these groups. So here's a bunch of groups that interact very closely together, and here are bridge people. And again, we can show these to people, and they say, I know who that is. So you have these strength of weak ties type of phenomenon that occur there. And then you have these other fields where you have these intensive collaboration between the groups themselves, and you don't have bridge people, you have many things going across. Often this is a graduate student of this person who now moved over to this group over here, who still co-authors with his or her colleagues over here, but works with people over here, and does the weak tie over there. So this is all documented in this Scientometrics article. And what's interesting, if you go one step further, is you can start to classify the nodes. So you can classify people into being non-hubs or hubs, and we have a whole classification of nodes and their proportion to the population. And you can really come up with a notion of who are the role players in this sort of interesting social network based on co-authorship. So the results here have been quite nice, and you can even extend that into the geographic realm and understand. So I think the yellow nodes are people in the United States. The blue nodes, no, the yellow nodes are people in Asia. The blue nodes are the United States. The red nodes are Europe, or something like that. But you can understand how geographic dispersion affects co-authorship. So we did all this work, and we were sitting around one day looking at this and saying, gee, those Asians really collaborate a lot. Isn't that interesting how much they collaborate? And we had this sudden realization, the potholes on the road to thinking this research was legitimate. It's the fact that often there are two people who have, there's one name who's really two people, and there's one person who often has two names. So you run into the reason that the Asians appeared to collaborate with so much with each other is that not all Si Wangs are the same Si Wang. Not all S Wus are the same S Wus. So we ran into a problem quite familiar to people, and people at Microsoft who have been doing academic search have seen, which is the name disambiguation and the name ambiguation problem. And it turns out that that problem distorted our results really badly, and we had to go back and spend 6 months working on the problem of author name homonymity, which is a very difficult problem. It's given the fact that features are very hard to extract from academic papers, and that the strength of those features, such as institutional affiliation, is very difficult to judge. It becomes quite a hard problem. So we have a paper that we published at JCDL this year that we're presenting at JCDL that talks about doing this with very sparse metadata. And the way we're doing this is doing it by co-author affiliations. It came up with very nice results. So if I have Wang, who published a paper with Lugosi and Warner, and I have the privilege of having a unique identifier, we can pretty reliably, if we have enough evidence, statistical evidence, disambiguate that from the paper by Wang, Zdanek, and Gagner. And that we can, if given enough overwhelming statistical evidence, we can say that these are different Wangs. And our results came up really nicely there. The problem, of course, that remains is the Wang, Sung, Kim, Yang papers, which we have. If you look at our results in the paper, you'll see we have really nice results for this world. This world is just. I mean, even so, we paid students we paid for about 100 hours of student work to do gold standard. And even the students couldn't figure out. I mean, just by searching all over the place, searching Bing, searching Google, whatever, they couldn't disambiguate these. So if humans can't do it, we have a hard time with machines. But just to show you the results here, this is red. These graphs are based on node role here. So these are the role. And what's important here to recognize is that since our co-authorship graph has different roles in it, the mistakes in one role are really bad than mistakes in another role. And can I write on the board? So if you have one of these subgraph, and you assume that person's let's say that's a person in role 4, which is a person that's a bridge. If that's really 5 people, that grossly affects the topology of your graph. So we have to be careful that our disambiguation techniques are biased towards our type of graph. So the problem becomes more complex. But in any case, without fully describing this result thing, the reds are really bad disambiguation problems. And you can see with our disambiguation algorithm, there's very few reds left in here. So you can take a look at this paper. It reports those results. So to conclude on that, and then pass it over to Bernhard, our initial results show some very interesting different collaboration patterns between fields that rely on either individual achievement or collective achievement. And the collaboration patterns are quite different, and they point to a shaping of one of the prejudices we tend to have is that sharing is great. And in this world, sharing is not absolutely great, so the technology has to be adaptive to those type of field differences and cultural differences. I'll pass it over to Bernhard, and then I'll close up with a couple of last comments. Thank you.
Yes, thank you, Carl. I will now focus on one specific technique in the area of scholarly works and scholarly communication, which is annotation. And I will demonstrate one particular tool we built back in Vienna. I'm originally coming from Vienna, came to the US 2 months ago. So that's also the reason why I'm attributing my colleagues here in Vienna. But I will demonstrate basically our annotation tool and how you can apply it for one specific use case, which is the annotation of historic maps. So we will see later that this is actually also a use case which targets several domains, but it's a very interesting use case. In this demo, which I will give at the end, you will also see how we make use of the vast amount of data that is out there on this data web, on the linked data web. I'm speaking of DBPedia, Geonames, and all the other sources that are out there. We believe that this is quite an interesting combination, and that scholars as well as institutions running infrastructures where people can annotate could benefit from pulling in data from the data web. Okay, from Carl's talk, we know that communities are diverse. So the first question that usually comes up when I start talking about annotations is the question, okay, what is an annotation? And there are so many definitions out there in the literature, and definitions that you find might suit for one discipline but might completely be unsuitable for another discipline. So whenever it comes to designing annotation tools, annotation models, protocol, the first question to be resolved is always, okay, what is an annotation? It's a really difficult question. And I found one very nice abstract definition in Palmer's paper. It's in the references on my last slide. It simply says, okay, annotation is note-taking to manage, interpret, and coordinate sources. But I don't want to stick with definitions. I go on to some concrete examples. This is an example I took from a colleague from the Brown Digital Repository. There are people who have the possibility to annotate works from PQ to add their interpretations to ancient texts. So this is one facet of annotation in one particular community. The link to the slide is down there. Here we have another use case of annotations. This is coming from the Australian literature project, where scholars have the possibility to add, to annotate text passages and add additional knowledge to these passages. So here, for instance, somebody explains what the term young ladies means by means of an annotation. Here we have another example from the, I think it's a biochem domain. I took this example from a colleague from Colorado University. In this domain, they're annotating words within the text to learn more about the semantics of a term. So it's a complete different notion of annotation. And this is my very personal view of annotations, that the technique I use most often. It's actually the annotation of PDFs to mark important sections in this document. I think this is also a very important aspect of an annotation. Okay, so what is YUMA now? YUMA is a tool we built to annotate multimedia objects on the web. It's actually a web application which consists of a server component and several clients. The clients are media specific, so we have a client for video, one for audio, one for images, one for maps. And these clients can be used for different use cases. We developed this tool back in Europe in the context of Europeana. Europeana is the European Digital Library project, which aggregates multimedia content from cultural institutions all over Europe. So there's a really large pool of media objects out there which can be annotated by scholars, but also by normal internet users. YUMA is also open source software. It's available on GitHub. Anyone can pull the source code. We're also happy if somebody pushes or at least gives us some issues so that we can further develop this code. So it's completely accessible and free. YUMA is also, in our opinion, of course, an infrastructure for cooperative research, because people really have the possibility with those tools to add their thoughts, their ideas directly to the media objects. And this is a very important and communication mechanism in scholarly research. With this slide, I just want to emphasize that the demo today will be about historic map annotation, but YUMA is really more, it's a multimedia annotation framework. So we have web clients for annotating videos, audio files on the web, images on the web. The video and the audio client are written in Flash originally, but are currently completely rebuilt into HTML5. So we want to get away from Flash in this case. The image client is written in, at the end, JavaScript, but built with Google Web Toolkit, and the same is the case for the map annotation client, which I will show you later. why did I take the map annotation use case? I took it because it's a very interesting use case because it targets. I don't know how I get rid of this line. Okay. Because it targets quite different disciplines. You can study historic maps, of course, from a historic point of view to learn about how country borders have changed or whatever. But also from another point of view, you can study technologies that were used at a certain point in time to construct maps or to produce knowledge about geographical units at this time. Certain maps are also pieces of art, so you could also study them from artistic perspective. And of course, most importantly, maps are still the predominant medium to transport geographical information. But you see there's quite a variety of disciplines that are involved in this particular use case, and that's why we think it's quite interesting. Okay, but now it's demo time. I prepared a screencast which will show just start again. Okay, this screencast shows you how you can use our tool to annotate digital maps. For a use case, we took a map from the Library of Congress, so you should be familiar with the geographical region here. You can simply start annotating this map by giving the URI of this map to our annotation tool. Here I'm zooming in and zooming out of the map just to demonstrate that we actually used high-resolution maps tiled into smaller images, such as the same way as we tile normal maps. And we support two types of annotations. The first type is geo-referencing. The second type is semantically augmented annotations. And I start with the first type. The geo-referencing annotations allow you to associate geographical points to ancient maps. So here, for instance, I identify the city of Philadelphia on my historic map, and I say, okay, this point is Philadelphia. I enter this information in my annotation box. The system automatically fetch geo information from Geonames to add this geo information to this control point. And to properly geo-reference a map, you need actually 4 control points in order to project today's coordinate system on the coordinate system of this map, of this ancient map, so that you can do geographical information system features on geographical maps as well. So here, I'm annotating the city of Detroit. I say, okay, this is Detroit, and I create later on one more point, one for Chicago, because I know that at this point where the river flows into Lake Michigan should be Chicago. So I created 4 geo-referencing annotations for this map, and now I somehow projected today's coordinate system on this map. And now I can overlay any kind of KML vector data on this map. For instance, here I'm selecting country borders, a very simple example, but it shows you what you can do with it. And this allows you to nicely embed an historic map into today's map. You can imagine that instead of this map, you can take any other map. Okay, now the second type of annotation, which is the semantically augmented annotation. This allows users to add commands to regions on a map, and I created a command for the region I know best in the States here, which is the Finger Lakes region. I just moved there recently. So I'm saying, okay, this must be Cayuga Lake, at least one of those lakes. And then I add my knowledge about this region. And you see that in the background, there are some tags popping up. And these tags are actually suggested based on the geographic region this annotation region covers, but also on the annotation tags that the user enters. So it's analyzed during the annotation creation process, actually. And these tags are actually not just string tags. These are links to resources on the web, to resources in Geonames, but also to resources in DBPedia. DBPedia is the structured version of Wikipedia. So we give the user the possibility to check tags which are, in his or her opinion, relevant for this annotated region and gain additional semantic information for this region, but also for this map. So for instance, here, there are some false positives as well, like the Australian capital, but Israel Cornell is the founder of Cornell University, is somehow related to this region. Central New York is obviously related. Cornell University is in this region. Cayuga Heights is part of Ithaca, so these are also related. Yeah, and the important thing is that these are not string tags. These are links to DBPedia, and behind those links is extremely valuable semantic information which we can pull into our system. And I will show you later on how the system, or actually the organization running the system, oh dear, can benefit from this at the end. Okay, so you see we created the annotation. At the same time, during the authoring process of an annotation, we create links. And we believe that these links have quite a high quality because it's the annotation creator who acknowledges the semantic validity of a link. Okay, what we do now is we search for annotation. It's a very simple use case, but before we search, I show you that this data record has been created. This is the annotation I created before with the text plus the links. You can open it again, see the annotation. And now, just let's assume we are a user and now we want to search for a map. If we don't have any metadata or any annotations, we won't find anything. With annotations, we can at least search over information the user has provided. We will find something when we search for Finger Lakes because user wrote it's about Finger Lakes. That's trivial. We will also find something for Cornell University because in the text, that's trivial. But now we start searching in different languages. So I'm searching for Lago Cayuga, it's Italian. I also find this record. Now I'm searching in Finnish. I also find this record. Now I search in Japanese. I also find this record, and the same for Chinese. So one of the benefits of pulling in those data from DBPedia is that you can enable a very simple multilingual search feature, actually. And this is especially important in Europe, where we have 20 whatever languages just in Europeana. Okay, now I show you that all the annotations that are actually created by the users are shared as linked data on the web, or at least as data on the web. So each annotation gets a URI and is dereferenceable via HTTP. So you can simply send an HTTP request against an annotation, and you receive the complete annotation represented in RDF, in this case, via HTTP. We also support JSON, if somebody wants to go for JSON. Okay, so you see, with this annotation tool, we tried two things. We tried to make use of data that is out there on the web, which is very nice for use cases like Europeana, where we have this multilingual search problem, because we can exploit the information a user gives us. But we also give something back. We give back the knowledge the users created in terms of data. And this is a nice cycle, I think. I just go back to my presentation. Yeah, here is the demo again, in case you want to see it. I think you noticed maybe the data model we used for the annotation. That is not something we invented. It's something which is coming from a collaboration which started approximately 1.5 years ago here in the US and also in Australia, which aims at facilitating some interoperability environment for annotations. So the goal is really to make annotations available in a way so that you can take it and transfer it to another system. For instance, it should be possible to integrate an annotated map into some e-learning system. And this, of course, requires some shared data model, and the Open Annotation Collaboration is working on that in the moment. And we are also somehow involved there. Yeah, this is how the annotation graph looks at the moment. It's an RDF graph. You have the concept of an annotation. You have the concept of the body of an annotation, which is more or less the content the annotation contains, so the text I entered plus the links. And you have the concept of an annotation target, which is actually the medium out there on the web, which has been annotated. And you see that everything has URIs and everything is dereferenceable via HTTP. Yeah, future work in the next 2 years at Cornell. I would definitely like to further develop this annotation, this map annotation use case. Maybe set up some repository for historic maps, where people can annotate maps and add their knowledge to maps. It would also be nice to integrate this with systems that support today's map, like Google Maps or Bing Maps or whatever, because it would be, in my opinion, very interesting for the user to see for a certain location, okay, what was this location in 1769. So this could be a very interesting future work. I also would like to enhance the semantic augmentation a bit. At the moment, it's really simple and straightforward. We just pull in data from DBPedia, index the label, and just search over the labels. That's trivial. That's not optimal because it produces still a lot of false positives. So we would like to integrate also some relevance feedback mechanism which improves the tag proposal over time. That's one of the ideas. And the second big idea is to also think how some of those two techniques, especially the semantic enrichment technique, can be integrated with scholarly publications. So when somebody writes an article, how we can encourage the author who writes the publication to create links to external resources on the web while he or she is creating the paper. So this is my future work here at Cornell, and I'm always happy to get some input. Thank you.
One more thing. Okay, so if I may.
Yeah, yes.
So what do? I just plug in?
I think so.
So I wanted to close up with just one more piece of work that fits into this whole area that we're doing. This is work that we presented just recently at the Web Conference in India, and this is work with Yuk-Young Jo and John Hopcroft, who's in computer science. And this is really to take a look at a field like computer science and understand how topics develop and ideas develop over time. A lot of the work that's been done in this area basically has either fixed time slices or has a fixed set of topics to see how they develop. And there's been some certainly nice work there, but what we wanted to do is not at all define the time slice, that a topic could originate at any point in time, and it could be the topic could be anything, that basically no learning at all is totally unlearned technique. So this is sort of a slightly representative graph, but we want to understand this notion of, as time progresses, this growth of a topic into separate subtopics, or even the merger of multiple topics into a single topic. And the example we use all the time is this notion of link-based searching, which arguably was sort of Page and Brin and John Kleinberg, which sort of combined, sort of these very interesting areas of IR and graph theory and other things into an interesting thing. And then these even more complex topic creation things. So topic creation configurations. And we have a technique that essentially does a statistical analysis of the text of the papers. We use just the abstracts, and walks through time, looks through the corpus, and notices when a paper appears that has a statistically different characteristic than papers that preceded it. And also then that statistically different fingerprint carries on to follower papers. So our definition of a topic is something that differs in a way from previous papers, but actually carries that difference persists over time. And it's sort of an interesting model. And then also the linkage between topics is a statistically significant resemblance between these two separate topic areas. So we came up with some really nice results here. And I'll just briefly put up, this is a little bit hard to read, but this here is a breakdown of the ACM corpus since 1972. And you can see here, and this is actually, we deduced these by hand looking at the papers. But future work is to be able to cluster these areas. But you can see the development of graphics over time, development of database over time, and you can also see the linkages between areas and how they sort of grew from each other. So, and what's interesting here again is this is the nodes here are topic areas. They're not specific papers. They're a group of papers that fit into that topic area, and then the linkages are the linkages between topic areas. So the results came up really quite nicely here, and there's a paper in the web conference this year. So to close up, last slide. A lot of the work that we've talked about and that we're doing is sort of combined into this large project called the Data Conservancy, which is one of the NSF-sponsored data curation projects. And I thought I'd just end up by pointing out a paper that sort of gives a large overview of understanding why cyberinfrastructure is so hard. This is a paper that was accepted this year and will be presented at JCDL by my graduate student Karen Patsky and I. And really looking at this whole cyber infrastructure problem as a socio-technical problem that really needs to be understood in the large to be able to work well. So with that, we will discuss our end.
Thank you.
Thank you.
I got a question.
Yeah, yes.
So it's a question, and perhaps a rude one for both of you, but you started your talk by saying, in the beginning of your career, you did these different efforts, and some of them didn't grow like you would have hoped or expected, protocol-based, etc. And I'm trying to think, in your part, making reference to the open annotation work, how are you able to think about those situations, and how do you make sure that open annotation does scale, does work? That is, you run the risk of, again, developing a system that is hard for scholars to use. And I'm trying to figure out, you're not alone. Obviously, there's thousands of people around the world coming up with similar systems every day. How do we address that and prevent that from happening?
Yeah, there was a workshop 2 weeks ago where exactly this question came up: how to assure that this model actually really fits a discipline, and the data created by one discipline can really be used by other people in this discipline, and how cross-disciplinary work should be enabled. Yeah, and the solution seems to be that this annotation model will be really something extremely generic, and that different disciplines need to create some kind of application profiles for their specific needs. For instance, we have the whole community of geo-information people who are annotating whatever with GIS coordinates, and they need some very specific aspects to be covered by the model, and they probably will need some extensions of this model. So it seems that there will be some kind of a core and extensions. So
let me, because I have another answer. I don't mean by anything that we're saying that the effort to create technological solutions is useless. The problem is when you go from the low-hanging fruit, the generic, and I applaud the generic efforts. I think they make a huge amount of sense. And a lot of the work that I've done and other people have done, I mean, certainly you'd be pointing the finger at Tim Berners-Lee and say that was a foolish effort if you say that these things don't work. But there's the sort of the hard balance between generic and too much specificity. And we haven't found on that spectrum, it's easy to do the generic things, like OAI, PMH. there's an example of something that works relatively well that does a limited amount of stuff. As you sort of move up the functionality spectrum, it becomes very hard because then you start to clash against specific cultural notions. So our grand notion of, this great, the fourth paradigm science that we've talked about all along, when we'll be able to do these wonderful this great synthesis of data from different domains and use it in great new ways, is a vision that's great, but it's going to take a heck of a long time in understanding to get there because it's not the low-hanging fruit. It really clashes in this world. Yeah, Mark?
You, Carl, in your talk, you mentioned how the large publishers, such as the Royal Society of Chemistry, the American Chemical Society, actually inhibit collaboration. In your opinion, what could they do to facilitate that collaboration? Is there a magic bullet? Is there a low-hanging fruit?
Or is there a bullet? I think it takes, Mark, I don't have a great answer, but my sort of intuitive thinking while talking answer really relates back to the same problem the music industry is having. It's sort of understanding what your value add is and distinguishing that from the data level. That the publishing industry would be wise to think of themselves as service providers on top of a data layer. And that the data layer the data shall be free, and he or she who creates the best services wins the capitalist game. And the ACS, like the music industry and the movie industry has tried, the entertainment industry has tried to embrace this vertical thing, which includes the data and all the services. And they're inhibiting scholarship by doing that, and they will lose eventually that battle. So I don't know if that's, yeah, Curtis.
I like the idea of annotating lots of different media, but there's always the challenge of the separation of the media from the annotation. And with both, you can put some in, and the ideal of some of these formats would then be able to accommodate both, at least a facsimile of the annotation, and then also have it separate as well. I've seen that. But do you have an approach in your annotation and how you make sure those sort of stay and persist over time with the media?
I don't have, but there is a group at Los Alamos working on a project called Memento, and they added the concept of fixity to the annotation model, so that you can at least capture the time, the time actually when the annotation was, the time when the annotation was created for a certain medium, so that you can, if a medium disappears, at least look it up in Web Archive or somewhere else. So that's one of the ideas, so that you can go back in time and retrieve the annotated resources in case it disappears.
So that's a very cool project. Yeah, but that's when something was annotated. But I guess the question is, if I've richly annotated the thing and I've turned out to be the world expert on this document, but the annotation is separate from the document itself. If your system dies, then I assume we have to figure out how to get that data back associated with it, as there are these other systems that the media ends up moving through in its normal path of usage, both publishing, consumption, things like that.
Those questions are definitely not part of the model. Yeah, but I mean, at the end, annotations will be web resources just like any other web resources, and the idea is to, at least in my opinion, I'm not speaking for the whole consortium here, to reuse also techniques that are used for the same problem in the web context, I guess. Also for security and authentication. It's not part of the model, it's really in the web stack. And
I mean, at the simplest level, people have the same problem with their own photos, and then they annotate them, and how do you ensure that those annotations stay with those photos? At least with a few tags, you can embed them within the headers of these image files. But when you talk about video and other formats that are dynamic, or like the rich map annotation, which I love, how do you associate that with things that are, those are image tiles, and the master one, there's lots of interesting complications.
The current solution have to make sure that the URI of the annotated media object remains dereferenceable and returns the representation that it was at the time of the annotation. Yeah.
So at least the pointer, right?
Yeah, that can happen.
Bernhard, I have a question. So, is anybody in the annotation consortium doing work on automatically connecting annotations to things? So, when you were talking, I was thinking of Twitter. And my big complaint about Twitter is Twitter alone is an incredibly decontextualized thing.
Yeah.
But I am basically annotating. And there's lots of examples. I mean, the walled gardens of the web are actually connected in implicit ways. And is anybody doing work in taking the annotation model and using it for those types of...
Yeah, I think if you look up the standard or the alpha version of the standard, there's the Twitter example there, because a tweet has got a URI and you can use it as an annotation on something, so it's considered, yeah.
Yeah, okay.
When you're using like Bitly or things like that to condense them, then that becomes an intermediate or pointer.
Right.
Which if they disappear, then you've lost all your connection.
right.
Yeah.
So it's how do you ensure the persistence of the connection between the annotation, which is so important, sometimes more important because a lot of times with digital files you might have copies of things.
Well, you know, in that realm, you know, the great controversy when they threw out library cards in the libraries,
Right.
where the library cards had these wonderful annotations, or the smudges. Oh, yeah, that's a wonderful example of annotation that was not intended to be annotation. Yeah.
But you're actually targeting one of the big problems of this whole data on the web discussions, the problem what happens if the links are gone.
Yeah.
And they're...
Anything else?
No, we'll just end on that eternal problem.
Thank you all for coming.
Well, Bernard and Carl, thank you very much.